Introduction to recovery. Recovery is the process of all the factors contributing to exercise returning back to their original values. These factors can be things such as breathing rate and blood pressure returning to normative values, as well as things like the resynthesis of ATP that has been used during exercise, as well as glycogen and fat stores. There are two stages of recovery that consist of the fast and slow components of EPOC. Fast components is also known as the alactic oxygen debt. This is the amount of oxygen needed to synthesize and restore muscle stores, which are ATP and creatine phosphate. Slow components, also known as the lactic acid oxygen debt, is the amount of oxygen required to remove lactic acids from the muscle cells and the blood. Recovery is needed in order to allow maximum performance in physical activity, such as the resynthesis of ATP, as well as also building back up depleted stores such as glycogen stores, which are vital for exercise. Different sports and different events will require different things from recovery. For example, an activity using the lactic acid system as the dominant system, such as the 400 meters, would need a long time to recover and would also demand other things in terms of recovery, as this would have produced a large amounts of lactic acid and therefore would cause a lot of fatigue. However, other physical activities such as marathon running would predominantly use the aerobic system, however would also demand a lot in terms of recovery, as they would have other effects on a person, such as the depletion of carb stores and more. In terms of alactic fast recovery, this specifically applies to factors which recover over a much less significant time period. These, for example, within 2 to 3 minutes after exercise, our bodies will have taken in an additional 1 to 4 litres of oxygen, which is used to resynthesize all our ATP/PC stores, as well as to replenish all myoglobin found in the muscles. These are fast recovery factors that take place over a short time frame of 2 to 3 minutes, and in terms of recovery are useful, as these factors are necessary in order to exercise. As well as this, in addition to the oxygen that the body takes in, is needed so that the body can resaturate hemoglobin and therefore supply all the blood and muscles with oxygen needed in order to successfully restore all the factors and help us recover. On the other hand, this lactic acid slow components of recovery consist of factors that will take longer time periods in order to recover. For example, after exercise, our bodies will require an additional 5 to 8 litres of oxygen in order to remove lactic acid from the body, as well as maintain ventilation, as this would have dramatically increased during exercise and also maintain circulation and body temperature. A key factor to this particular long-term recovery is to do with what happens to the lactic acid after exercise and how we get rid of this buildup of lactic acid. After exercise, when we react lactic acid with this high volume of oxygen, we can convert this into pyruvic acid, which can then be made into acetyl coenzyme, which allows this to then re-enter the Krebs cycle and therefore start producing more ATP. This lactic acid can also be converted into 4 other things. These consist of carbon dioxide, which is exhaled out, H2O, which is exhaled as water vapor, glycogen to make energy, glucose stored from energy, and protein that can be used as a fuel. This all occurs in the slow components of recovery. The lactic acid section is slower and longer recovery process, lasting anywhere between a couple of minutes to many hours. There are 3 main things that will happen during this process. These are the removal of carbon dioxide, removal of oxidized lactic acid, and the replenishment of muscle glycogen stores. The replenishment of muscle glycogen stores will take a lot longer, around 2 hours to a couple of days. This can be seen in the bottom right graph, where it will take about 2 days to fully restore all the muscle glycogen stores. Short duration, high intensity exercise like the 800 meters, restoration can take up to 2 hours. Prolonged low-intense aerobic activity such as a marathon, restoration can take days. High carbohydrate diets speed up the glycogen recovery process. As we can see in this top graph here, this is PC/ATP being restored over a short time period of 120 seconds to be 100% restored, which is why it is a lactic fast recovery component, as this happens over a very short time period. Oxygen deficit and difference in EPOC. During submaximal steady state exercise, we can see in the graph above labelled Figure 1 that during this steady state exercise we can see a much smaller oxygen deficit here, as well as a plateau in VO2, which you can see here. This is due to the fact that this particular graph is to do with steady state exercise, and therefore the person will be working at a steady and continuous pace, and therefore VO2 will plateau and stay the same, as we can see in the graph above. In terms of EPOC and recovery of this particular type of exercise, we can see less VO2 consumed, therefore meaning that recovery is faster and more efficient. Another contributing factor towards why recovery factors occur faster during submaximal exercise is due to the fact that this particular form of exercise will be using mainly the aerobic system to fuel and create energy for this system. This therefore produces less lactic acid, and as you can see, recovery time is much faster compared to this graph here. On the other hand, we can see a much greater oxygen deficit in the maximal exercise graph. As well as this, there is no plateau or steady state visible in this graph like we can see in the submaximal graph next to it. As this particular graph represents maximal exercise, this means a person would be working as hard as they can and predominantly working anaerobically. This means that they are not using oxygen to produce energy, so therefore will be using the lactic acid system in order to achieve this, which would mean a considerable amount of greater lactic acid buildup. This, in terms of EPOC, would mean that recovery would take longer due to this lactic acid buildup, as well as meaning a larger VO2 of oxygen would be needed to be consumed in recovery in order to account for metabolic needs that have drastically increased from maximal exercise and need to gradually decrease in order to recover. As well as this, more oxygen is needed in maximal EPOC so that all this build-up of lactic acid, due to the lactic acid energy system being dealt with / removed. Therefore, recovery takes longer in this particular type of exercise, as shown in the graph here. Metabolic needs. Metabolic needs is to do with cardiac output, heart rate, and ventilation and temperature after and during exercise. The graph above shows the slow and steady decrease in internal temperature after a person has stopped exercising. This is relevant to metabolic needs, as these needs will follow a particular pattern after exercise, in the sense that they will not just dramatically decrease out of nowhere from point A to point B, but these factors will gradually decrease, as shown, as to aid recovery, and you can see in the graph above. The reason breathing rate and ventilation and cardiac output will slowly decrease is due to the fact the body, even after exercise, still requires great amount of oxygen, as stated previously, in order to help the body recover as efficiently as possible and remove waste products such as lactic acid and CO2 and convert these either into the 5 things lactic acid can be converted into or exhale out CO2.